In this presentation, I'll be explaining the different power converters that are using in renewable energy system. This is the electrical schematic diagram of a grid-connected variable speed wind power system in which the wind is hitting on the blades of the windmill as such here, and that is coupled to that windmill, that turbine, that is wind turbine is connected to the generator, and here you will be getting an AC output voltage whose voltage magnitude and frequency may be changing. Therefore, we have to convert this variable voltage and variable frequency into a fixed voltage and fixed frequency. Therefore, here the first we require a rectifier. Here the rectifier rectifies the variable voltage, variable frequency signal into a DC quantity. It's a unidirectional quantity that is done by a rectifier. Then there is a filter mechanism. It's a LC filter is provided, and that filter filters or that converts this, the unidirectional voltage which is varying into a constant DC voltage. That is done by this filtering, and that DC voltage is again converted into AC voltage, and which can be connected to the grid, that is by the inverter. Therefore, basically there are, of course, there is a rectifier is there, and there will be a filter will be there. Sometimes there will be a DC to DC converter also will be there. That's not included in this one. And that DC output is converted into AC by using an inverter. Therefore, here, of course, there are different controls like pitch control is there. Of course, the power control that is that controls the rectifier unit. And here there is a inverter control unit that converts the DC voltage into AC voltage that can be connected to the grid, and the voltage information as well as frequency information is to be given as such. Therefore, this is a block diagram representing the electrical schematic diagram of a grid connected variable speed wind power system. Therefore, that requires a rectifier, and of course the inverter is required, and there's a filter LC filter or any filter is required that makes the variable unidirectional voltage into a constant magnitude. Now, continuing the power converters in a renewable energy system, we are considering a wind energy conversion system, in which, as we have already explained in the previous presentations, this is a doubly fed integration generator DFIG, and in DFIG, in wind turbine blades or wind turbine is there, that pitch control setup is there. Then there is a gearbox mechanism that changes the speed, and that is coupled to the rotor. And again, there is a stator is there. The rotor, it is a one rotor type, or it is a slip ring type. Therefore, that the voltage of the rotor can be say variable voltage and variable frequency signal is available at the rotor winding, and the stator is directly connected to the grid through a transformer. Therefore, in this case, the variable voltage, variable frequency that is available at the rotor of this doubly fed induction generator, that is to be converted into a fixed voltage, fixed frequency. Therefore, there are two stages is there. This variable voltage, variable frequency, first it is converted into a DC quantity by AC to DC, or that's called the rectifier. So rectifier unit is there that converts the variable frequency, variable voltage quantity into a fixed DC voltage, and there is a capacitor to make the voltage stiff, and in certain case this voltage is to be changed by using the chopper is the DC to DC converter chopper is there. Of course, that DC input is given to an inverter that converts the DC quantity into AC quantity, and that AC output is connected to the grid through the transformer. Therefore, this part is the inverter, and this is the rectifier. Under if the speed of the rotor is more than the synchronous speed, super synchronous speed, the power from the rotor or the energy from the rotor is injected into the grid after by this conversion. First, it is converted that into a DC quantity by this rectifier, and then that DC quantity is again converted into AC quantity and connected to the grid. Therefore, the power converters required here is that DC to AC converter is required, that is, I mean, AC to DC converter, that is AC to DC, that is called the rectifier is required. Then DC to DC converter chopper is required. Therefore, the various power converters used here is, one is the AC to DC converter, that is a rectifier, AC to DC converter. Then DC to DC converter, that's called the chopper. The whole level of the DC voltage can be changed by this chopper. And this DC is again converted into AC by using inverters, that is DC to AC converter inverter. That's called the inverter. For a rectifier is the control rectifier is the, then inverter is the, a chopper is the. Basically, this unit that is I mean that shown as the here. Therefore, this part is the control rectifier. To that one rotor, I mean the rotor windings are connected here. The same thing here. The rotor windings voltage is same as shown here, and that is same. That is made by, I mean, three legs are there. It's a three-phase and signal. That is why there are three phases are there, and in each phase there are two switches are connected. IGBTs are there, two switches in each leg it is there. Therefore, this is a control rectifier that converts the rotor variable voltage, variable frequency into a DC quantity that is available here. Therefore, the back-to-back converter in a double effect induction generator that is shown here, it is that consists of a control rectifier. That another one, this is an inverter or that converts the DC into AC. This is connected to the grid, and this is connected to the rotor winding. Therefore, the same thing is shown here. And basically, there are three converters that is using here. One is AC to DC converter, that's called the rectifier. Second one is the DC to DC converter, that's what called the chopper. And third one is called DC to AC converter, that is called inverters. Now, this is a diagram of a single phase full bridge converter. That is a single phase with a resistive load. This is a single phase voltage that is converted into a unidirectional voltage. This is the input voltage, single phase voltage that is here. There are four switches are using, that is thyristors, SCRs, T1, T2, T3, T4. T1, T2, T3, T4. And here the single phase supply is connected and load is connected between this one. Therefore, during the positive half cycle of the input, T1 and T2 are fired at certain angle, we call firing angle. For example, after this much time, these T1 and T2 are fired. Once these are fired, you will be getting the voltage same as the input voltage here. Then that negative half cycle that is getting turned off, and next the other thyristors, that is T3 and T4 are fired after again pi plus alpha. This is alpha, pi plus alpha. Therefore, during the negative half cycle of the input, these T3 and T4 are conducting. Therefore, again, since this is positive here, during the negative half cycle here, this will become negative and this will become positive. Therefore, T3 and T4 are conducting. There will be a current flowing through this like this one. Then again, the voltage will be positive like this one. Or a bidirectional voltage with a positive and negative quantity, it will be converted as a unidirectional voltage. This is the voltage across the load. It's a unidirectional voltage. And if you calculate the average value of this voltage, the average value of the voltage can be calculated as this equation 1 by pi integral alpha to pi Vm sin omega t d omega t. Very simple equation only. And then you will be getting it is equal to Vm by pi into 1 plus cos alpha. Or by changing this firing angle here, for example, if firing angle to 30, it will become 1 plus cos 30 comes. For by changing the firing angle of these thyristors here, you can change the average value of the DC voltage, average DC voltage that is available at the output can be changed. That is Vm by pi into 1 plus cos alpha. This is an example of a single phase full bridge converter that converts the AC single phase AC voltage into a DC or unidirectional voltage. That is average value of that one equal to Vm by pi into 1 plus cos alpha. Again, a single phase full bridge converter, instead of a resistive load, if you are considering an RL load, because normally if it is a motor type load, it is an RL load. Inductance and resistance that comes here. In an RL load, in of course we call continuous conduction mode. Here you will be getting the corresponding voltage will be like that one. This is the waveform of the voltage across this. This is the load. RL load is across the load. This is the voltage. Even negative half cycle of the input, this will be continuous to conduct. And here the average voltage of this, if you calculate the average voltage across the load here, it will become 2 Vm by pi cos alpha. Therefore, by changing the firing angle alpha, the average voltage of this one you can change. That is average voltage equal to 2 Vm by pi cos alpha. If alpha is less than pi by 2, you will be getting a positive voltage. If alpha is more than pi by 2, you will be getting average voltage will become negative. Therefore, you will be getting a variable DC average or average voltage here across the load as the firing angle changes. Therefore, that converts the AC input into a DC, a unidirectional voltage whose average value equal to 2 Vm by pi cos alpha. If you consider a three-phase full converter, that is 6-pulse converter it is called. This is actually what we are seeing previously. It is a three-phase quantity, that rotor voltage, that will be converting that rotor variable voltage, variable frequency signal to a DC quantity. That is this three-phase signal. Three-phase. In each leg there are two switches. Maybe here I have shown as silicon control rectifier SCR. In each leg there are two switches and three-phase voltage is coming. In doubly fed induction generator, this is coming from the rotor winding. Three voltages, variable voltage, variable frequency signal is coming, and that is converted into a unidirectional voltage. That is shown here. This is the voltage available across the load as such here, and the firing sequence of this one. The firing sequence is for each 60 degree that is fired here. Therefore, T1 is fired first. T1 is fired. After 60 degree, T2 is fired. Then T3, T4, T5, T6. These are T1, T3, T5, T2, T4, T6. The firing sequence is T1, T2, T3, T3, T4, T5, T6. Therefore, that's the firing sequence of these SCRs. And then you will be getting a voltage which are all unidirectional. And the average value or the DC value corresponding to this is given by 3 VML by pi cos alpha. VML is called the maximum line voltage. Therefore, by varying the firing angle alpha, the average voltage can be changed. That is, this is case of a three-phase full wave converter or the 6-pulse converter whose average voltage equal to 3 maximum value of the line voltage, 3 VML divided by pi into cos alpha. The next converter to be considered here is a DC to DC converter. That is, input is a DC and output is also DC. Previously, we have seen AC input and DC output. But here, the input is DC and output is also DC or DC to DC converter. It is, you can get a variable DC output voltage. That's called, this is a step down chopper, or this is step down means where the voltage is getting down or getting reduced here. About the basic step down chopper diagram is like that one. This is the voltage that is at the input side. There's a switch is there, and there is a load, RL load is there. There is a freewheeling diode is there. Therefore, this is the diagram of a chopper. And in that case, the same thing concept is as a converter, we call it as a buck converter. Step down chopper, the voltage is reducing and corresponding output voltage is given by the duty ratio into V, where duty ratio means this switch is, when switch is on here, the diode is reverse bias and there will be a current flowing through the load. And you will be getting the same voltage as the supply voltage, that is same as this one. When switch is off here, due to the freewheeling action of this through the diode, you will be getting a zero voltage. Therefore, by changing the duty ratio, which is nothing but on period divided by total time period, by changing the duty ratio, you can vary this is the average voltage, DC voltage. That average voltage can be changed by varying the duty ratio. The same concept is, that is a buck converter. So when you are going to a buck converter here, step down converter, here same as switch is at the input side. There is a filter is there, LC filter is there. There is a load is there. There is a feedback diode is there. When switch is on, the voltage will be equal to the voltage at the input of the filter is equal to the same as the supply voltage Vs. And when switch is off here, that will be circulating through that one. Diode drop is, we can neglect. Suppose that will be 0. And this filter will be filtering the DC quantity. Therefore, you will be getting the average voltage at the output of this one. And this is the average voltage at the output of the load. Or that is, that average voltage is given by D times VD, where D is called the duty ratio, which is nothing but on period divided by total time period. That is, on period divided by the total time period is called the duty ratio. So that times input voltage VD or VS, whatever it is, that is the output voltage. Therefore, by changing the duty ratio, you can vary the output voltage for a given input voltage. That is, but always D, since the D is maximum value equal to 1, cannot be obtained, less than 1, you can get an output voltage less than the input voltage. Therefore, that is why it is called a step down chopper, or this is called buck converter, a step down converter. Therefore, the output voltage varies linearly with the duty ratio of the chopper, and the output voltage can be controlled in a range. Output voltage is equal to that is between V0 will be less than the input voltage and more than 0 volt. That can be varied in linearly. This configuration of the chopper is also known as step down chopper, or as a converter we call it, right? It is a buck converter or step down converter that reduces, or that step down the input voltage to an output voltage which is given by the relation V0 equal to D times VD. So that is a DC to DC converter, step down chopper or step down converter or buck converter, same topology. Another type of DC to DC converter is called to step up chopper, that increases the voltage. That is, here output voltage will be more than the input voltage. The circuit diagram is slightly different. Here inductor at the input side, switch will be across this one, diode is like this one. Here the output voltage and input voltage, they are related by output voltage equal to 1 by 1 minus D times V, where D is called the duty ratio of the switch. That is on period divided by total time period. That is the duty ratio of the switch. Therefore, if you, for example, if you select D equal to 0.5, 1 by 1 minus 0.5, or that is equal to 1 by 0.5 or 2 times V, output voltage will be 2 times the input voltage. That is why it is called step up chopper. Output voltage equal to 2 times if D equal to 0.5. Therefore, by varying the duty ratio here, you can vary the output voltage, which you can increase the output voltage for a given input voltage. That's called a step up chopper. Same in converter case, in boost converter, same as this one. Same here, inductor at the input side, a switch is there, a diode, a capacitor. Again here, the relation between output voltage and input voltage is given by 1 by 1 minus D, or output voltage equal to whatever the input voltage divided by 1 minus D. Therefore, by changing the duty ratio, you can vary the output voltage for a given input voltage. Or in this case, since output voltage is always more than the input voltage, we will call it as step up chopper or step up converter. That is called boost converter. Therefore, that is the second type of DC to DC converter. First one is the step down chopper, or it is called buck converter in that as a converter. And here it is called step up chopper, or its corresponding converter, it is equal to boost converter, that increases the output voltage for a given input voltage by the ratio 1 by 1 minus D, or V0 equal to VD divided by 1 minus D. As I already told, for example, if D equal to, you are keeping 0.5, output voltage is equal to 2 times the input voltage. V0 equal to 2 times VD. The third converter is called input is DC and output is AC, or it is called DC to AC converters. That is, they are called inverters. Input is DC and output is AC, inverters. Of course, there are two types: is the voltage source inverter, VSI, and current source inverter. If you come to the voltage source inverter, this is a single phase voltage source inverter. This is the input voltage, and here, of course, as already I told you, there are 4 switches are there. Here it is marked as S1, S2, S3, S4. There are 4 switches are there. But here always there will be freewheeling diode. We have to connect, because the load will be having an inductive load type, means that there should be a part should be provided. Therefore, a freewheeling diode will be, or freewheeling or feedback diode. Can say that feedback diode should be provided across each switch here. Therefore, that is provided. Therefore, this is a circuit diagram of a single phase DC to AC converter. It's also called H-bridge converter. Inverter. Of course, it's an inverter that converts the DC into AC. The load is here. Therefore, when the switch, when you want to have a positive voltage here, these 2 switches, S1 and S2, are closed, and then you will be getting a positive voltage across the load. Therefore, the path is like this one. You will be getting a positive voltage V, and to get a minus voltage, negative minus voltage, these are switched off, and other two S3 and S4 are switched on. Then you will be getting a voltage here. It will become minus, and here will become you will be getting a negative voltage. Therefore, as you change, as the switches S1, S2, and S3, S4 are controlled here. The input DC voltage will be converted into a square waveform like this. AC output voltage. It's a square type inverter, and this is the current waveform that is the current flowing through the load. Therefore, this is a single phase full bridge converter that converts the fixed DC quantity into a AC quantity, AC voltage. In a three-phase DC to AC converter, three-phase inverter, it's called three-phase bridge inverter. It's a six-step inverter. It is called six-step inverter. In this case, there will be three phases are there. In each phase, there are two switches, like as we have already seen here. T1, T3, T5, T2, T4, T6. Therefore, this is the way in which it is numbered here. And across each switch, there will be a feedback diodes will be connected. That is, each switch, there will be feedback diodes. And this is the DC input voltage. And the load is connected between these are the 3 points. Or this load is connected like a star connected load. It is marked as such. And here the load windings or that are connected these points. Therefore, AC voltage is available here, and this is the DC input voltage. There are 3 legs are there. In each leg there are 2 switches, and across each switch there will be a feedback diodes. Therefore, this is a pictorial representation of a 3-phase bridge inverter that converts the DC input voltage into a 3-phase output. Therefore, there are 2 modes of operation in which we are considering a 180-degree conduction. Each switch is made to conduct 180 degree. Therefore, in 180-degree conduction scheme, each device conducts for a 180 degree, and they are turned on. Out of the total 360 degree, half the period each switch is conducting. Therefore, they are turned off at a regular intervals of 60 degree each one. Therefore, T1 is fired, then again 60 T1, then T2, then T3, then T4, then T5, and then T6, again T1. And each device is conducting for 60 degree. Therefore, the output, that is T1, T2, T3, T4, T5, and T6. This is a sequence in which the switches are turned on, and the output terminals are that is A, B, C. Here, output terminals A, B, C at the bridges are connected to a terminals of a 3-phase star or delta connected load. Therefore, this is basically a converting a DC quantity into a 3-phase quantity by using 3. Of course, legs are there. In each leg, there are 2 switches are there, and each in this mode of operation, each device or each switch is conducting for 180 degree. Now, continuing the 3-phase bridge inverter, as already I explained the previous slide here. This is the same 3-phase inverter, and I told you, each switch T1, T2, T3, T4, T5, T6, each switch are conducting for 180 degree. Or for example, T1 is conducting for 180 degree. Again, T2 is conducting for 180 degree. T3 is conducting for 180 degree. Like that, it is each device is made to conduct 180 degree. And the firing sequence is T1 after 60 degree T2, again T3 60 degree, T4, T5, T6, again T1, like that one. That is the firing sequence. Now, if that is fired in the sequence, you will be getting a voltage. If you calculate the voltage here, that is the voltage at this point with respect to the neutral, you will be getting a step like an AC voltage like this one. This is the voltage of the A phase, and this is the voltage of the V phase, and this is the voltage of the C phase. You will be getting a 3-stepped voltage, AC voltage, that will be available between the phases A and neutral, B and neutral, and C and neutral. Therefore, we are converting a DC quantity into a 3-phase AC quantity. This is a phase A voltage with respect to the neutral. This is a phase B, which is 120 degree apart with respect to the neutral. And this is the phase C voltage with respect to neutral, which is again 120 degree. Each phases are 180 degree apart. That's called the 3-phase quantity. Therefore, the DC voltage is converted into a 3-phase voltage by using a 6-step inverter circuit. Therefore, like that, we can convert a DC voltage into a 3-phase AC quantity. That is by what's called 180 degree method of conduction of a 6-step inverter. This is the block diagram representation of a double output induction generator with a current source inverter. Double effect induction generator itself. In that one, of course the stator is connected to the grid directly, and rotor, that is rotor is connected to the, for the two converters are there, as that is the rotor side converter, and actually this is actually the grid side converter, as we have already seen, converter 1 and converter 2. This is actually converting this AC quantity into DC quantity. Again, the DC quantity is converted into AC quantity by converter 2. Therefore, this is the block diagram as such. This is explained as a current source, current source inverter. Since it is a current source that we are connecting inductor, a large value of inductor is connected in series, so that will be a constant current. Previously what I explained is a voltage source inverter, in which we are making the voltage constant, and there we are using capacitor, but instead here we are using an inductor to make the current constant, so that here that constant current is converted into the, of course, that voltage, that the output of the voltage, say AC voltage is that is connected to the grid through a transformer. Therefore, this is a block diagram representation of a double output induction generator. It's called actually doubly fed induction generator with current source inverter. Therefore, this is a converter which converts rectify, and this is acting as a inverter.